concluded today's lecture just an hour ago. So that you all check the syllabus, the syllabus I'm going to talk about it, the midterm grades. Okay, so if you check the midterm grades a couple days ago, you'll find a grade, okay? This grades, the average of this grades was 71%, so, but some of you are very high, there's lots of hundreds, lots of people over 90, and lots of people under 50. So that's why the average is like kinda high, 71. As I said before, the exam was very easy, and don't expect this in midterm number 2, so you need to prepare yourself more because some of the questions are not gonna put them. There's 2 questions Professor Leon are gonna put them in the exam. So just brace yourself, study hard for midterm number 2. And if you have any basics that needs to be revised, you need to come from the spring break and have the full robust basics for the particle dynamics, because we're gonna start the rigid body dynamics, which is more difficult than the particle dynamics. So this is the very thing. Yeah, so the average was 71. And then I brought the average to 80%. So I did some linear curving to the grades. So we'll get some extra points. Some of you got 5, some of you got 10. So not all of you get the same amount of points because it's a linear curving, not constant. Like not everyone get 5 points. So I'm not sure if you understand the concept, but it's linear curving, okay? So this is the thing. I'm gonna distribute the midterm sheets after the class. If you have any questions, if you have any concerns about partial credits, come to my office and we can discuss it. Not here because there's a class here after our class. Okay, so this is the thing. Yeah, and a few announcements. The TA told me that some of you upload homeworks late, like homework 1 and homework 2, which were due like a month ago. They just uploaded. It's okay if you want to upload them, but let him know so that he can grade them, because he will not be able to know that you uploaded your homework. I believe that's all the announcement that I have for now. Yeah, and another one, as I said, like Professor Leon was gonna start like on Thursday, but I agreed with him that it's better that he start after the spring break, because the spring break is next week, so we don't have classes on next week. So he's gonna start the week after the spring break for 2 weeks. So he's gonna spend 2 weeks on fluid dynamics. Okay, so we have a class today and a class on Thursday with me. All right, so we will try to finish today the impulse and momentum. So as you guys recall from last time, we started to talk about impulse and momentum.
I leave
And momentum. And as you guys recall, for the impulse and momentum, that this is the main equation that the momentum mp1 plus the integration from time t1 to time t2, the forces dt is equal to mv2. So this is the general equation of the linear impulse and momentum. So, hey, yeah, focus with me. All right, so side talks, okay, stop. All right, so here we have the linear momentum at point 1 and the linear momentum at point 2, and this is the impulse that's what we were doing last time. This was the main equation that we had. And then we start talking about the conservation of linear momentum. So if you have 2 bodies, like we talked about, if we have 2 bodies, something like this, a body like that, this is body A, this is body B, and this is moving this way, and this is moving this way. So we have MA, VA1, and MB, VB2, VB1, sorry, and VA1 is bigger than V1. So when these 2 bodies at some point, because the velocity of particle A is bigger than B, so at some point they are gonna collide. So, and that's what's gonna happen. So we started phase 2, that these 2 bodies are gonna be something like this. And when this happens, we call this the deformation impulse. deformation impulse, look at this. Particle A is gonna have a force and impact particle B. So this is the force from particle A impacting particle B. So this is particle B. And particle B is gonna have a force particle B is going to have a force impacting particle A. So this is how it works. So two bodies are moving to collide. So particle A is going to have a force and hitting particle B, and particle B is going to have a force and hitting particle A. So this is how it's going to work. And at some point, both of them are going to have the same velocity. So they are going to like melting together, something like this. And both of them are going to have the same velocity for small amount of time. So both of them are going to have a velocity v, and we call this maximum deformation. Maximum deformation. And phase number 4, after the maximum deformations, they will try to get away from each other, something like this. And we call this phase restitutional impulse. Let me write it. Just 1 second. Yes.
What would we label phase 1?
Hmm?
What would we label phase 1?
Phase 1 is the initial impact.
Okay.
So, or we say before impact. Before impact. Okay. All right. So that's what's gonna happen. Particle A and particle B, they are gonna hit each other, and at some point they are gonna move together. And actually, the moving together depends on the elasticity of the impact. If they are elastic, they are gonna go away from each other right away. But if it's elastic, it's gonna move together for some longer time. And this actually explains, like for example, car crashes. For car crashes, it's plastic. Why? When a car hit another car, the impact, so this is one is moving this way. And actually that's represent a car crash. Like if two cars is moving, both of them are moving in the same lane. One of them is very fast, one of them is slower, okay? So this is the slower car and this is the faster car. And this one moved fast enough to hit the other one, and they were gonna move, it's called plastic, and it's gonna move together for some time. So it's gonna hit him, and both of them are gonna move the same way. But if we are talking about, and actually it's a plastic, why? Because there is some energy are like, both cars are deformed. So there's a plastic deformation happen to both cars, okay? So, but if we are talking about like elastic deformation, like the billiardo game with the billiards, like if we have a bunch of balls on a pool table and they hit each other, they don't move together. They just hit and they just restitute right away. So this is called elastic deformation. Okay, so that's what's gonna happen like in general. Like you have two bodies are gonna impact each other. They're gonna have a deformation, and this deformation depends on the degree of elasticity or plasticity of the impact. And then they are gonna leave each other at some point, and we call this restitution impact. So this is gonna have a restitution force, and this one is gonna have another restitution force. And if it's elastic impact, the restitution are gonna be the same as the deformation force. So F is gonna be equal to R. Both of them are gonna have the same value. But if it's a plastic, actually R is gonna be equal to 0. Why? Because they are not leaving each other, they are moving together. If there's R, they are gonna leave each other, if it's a perfectly plastic, okay? But there's nothing as perfect as it should be, so there's nothing is perfectly elastic and nothing is perfectly plastic, it's always something in between. Even the pool table balls, when they hit each other, it is not 100% elastic, maybe 99% or 99.9, okay? Okay, so this is gonna happen, and then phase 3, they are gonna leave each other at some point. And this is something here, and this is gonna move with MVA2, and this is MVB2, and VB2 is more than VA2. Okay, so this is how the central impacts happen between two bodies. And let me tell you something, as we said last time, that there's a conservation of linear momentum happens here. At this phase, like if we look, they started, both of them has MA1 and MB2. So we do the linear momentum is gonna be something like when we apply the conservation of linear momentum, we said that this is the rule, if you remember. The sum of all the masses multiplied by their velocity, initial velocity, plus the linear impulse from T1 to T2 for all the forces dt is equal to the sum of all the masses multiplied by V2. Looking here, I'm gonna apply it from this phase to this phase. So they are gonna, both of them has MA, VA1 and VB2, and at some point both of them have the same velocity. So when I'm gonna write this, it's gonna be M VA1 plus M VB1. That's what I'm doing. All the masses multiplied by their initial velocity. So this is mass initial velocity, mass initial velocity. It's gonna be plus, we have the linear impulse. Look at the linear impulse that we have here. We have F, and it's a positive applying on body B. So we have positive F dt. And the same thing, we have another F, but actually it's a negative F dt. So there's internal impulses that cancel each other. So this term is gonna be canceled. And this is gonna be 0, so we will be left out with the mass multiplied by the velocity v2, and actually both bodies have the same velocity after the impact. So this is gonna be m ma plus mb multiplied by the velocity v. Why? Because it's ma multiplied by v and mb multiplied by v. I take v as a common factor, so it's gonna leave us with this, and this is actually what we call the conservation of the linear momentum. So the momentum before the impact is equal to the momentum after the impact. So that what gonna happen.
Wouldn't it be NBV1?
Oh, sorry, yeah, this is. So we have MAVA and MBVB1. All right. But if you wanna, so this is when we talk about the system. What the system, all the particles that hit each other. If we are talking about the pool table poles, if one body is hitting multiple bodies, so it's gonna be all the bodies that are included in the collision. Okay, so we're gonna include all the masses multiplied by all the velocity at the initial phase is equal to all the masses multiplied by the velocity at the final phase. If it's more than one body. Okay, but if you want to look at only one single body, not the whole system, because we looked at the system. Why did we look at the system right now? Because we are looking at two bodies hitting each other. So the mass and the sum of the momentum from this body is transferred to this body. Like let's say that the velocity of this body is 0, and this body have a very high velocity hitting this body. What is going to happen? Is this one is going to have the same speed as the initial one? It's going to have bigger or lower speed or lower momentum. It's the same thing. So this is still not moving, and this is moving and hitting this body. It has a momentum 100. Because this is going to be 120 or 50. 50, right? This one is 0 momentum. It's going to have more than 0. So that's the conservation of linear momentum. Some momentum from a body that had a very, very high momentum hitting a body that is still and giving some momentum to the other body. That's what we call the conservation of linear momentum. So momentum of the bodies before the movement or before the collision is equal to the momentum after the collision. and the impulses is canceled. Why? Because the forces are opposite to each other. So that's why they cancel each other. So there is no impulse in the conservation of linear momentum equation. But if you want to look at one single body, how the linear momentum relationship with the impulse look like, you can take this body alone, A, and look at its linear momentum. So you can say that MA VA1 plus the integration of the force dt is equal to MA VA2. You are looking at only one single body. The momentum of the body, A, before the collision, plus the impulse happened on this body is equal to the momentum after the collision. That's if you want to look at one single body. But be careful because body A has a force in this direction from B, so it should be negative. So this should be negative like this. Why? Because the force is in the other direction. And that's what's going to happen. Like you have a very high momentum of body A, okay, and getting a force from body B to decrease the momentum and make it less. You guys remember we have a body that is not moving and a body that is moving has a very high momentum. What decreases the momentum of this body from 100 to 50? Because it got some reverse impulse from the other body, this one, okay? So that's how it looks like. But if we look at body B, it's gonna be MB VB minus or plus.
Would it be plus?
It's gonna be plus because it's the force coming from A to B, the other direction. So this is gonna be plus F dt MB VB2. And that's why body B had much higher momentum, right? Because it got a plus component from the impulse, okay? So that's why this is minus and that's why it is negative. All right? Okay, I had, oh yeah, let's talk about the restitution coefficient. Coefficient of restitution. So the coefficient of restitution, let's talk about it, but before I do this, I wanna do something. Okay, so I'm gonna look at this phase with this phase. This is as the initial, and this is as a final, like both of the two bodies are moving together. Okay, so at this phase, the phase from phase 1 to phase 2, if we are looking at body A, so the mass of A multiplied by the velocity of A1 minus B, let's call this B because I name it in the, you can call it C, but it's in the notes is B, okay? So I named this force F, in the notes it's B, okay? So suppose, let's call this F. F dt is equal to the mass A multiplied by the velocity V. This is the final velocity, like both bodies are moving together. So this is the initial velocity V1, and this is the final velocity V. And after they leave each other and the restitution happens, V is the initial velocity, and there will be a final velocity VB2. So the velocity happened on a transition. VA1, and then both of them are moving together, V, and V2, V2. So we can say here that MA multiplied by V minus the restitution force, because there's a different force that caused these bodies to leave each other. As we said, that R is not gonna be bigger than F, okay? It's either equal or less. And if it's equal, that means it's elastic. So both bodies are gonna leave each other. And if it's less, so it's elastic. And if it's a zero, so it's a perfectly plastic, okay? All right, so when this body are moving together, there's a restitution, and this is dt equal to MAVA2. So this is phase 1, when there's a deformation impulse, and this is phase 2, when there's a restitution impulse, when they hit each other and then when they leave each other. So the coefficient of restitution is the ratio. We call this C or E. The ratio between the restitution impulse, R dt, and B or F dt. This is the restitution impulse, and this is the deformation impulse. Okay? The ratio between the restitution impulse and the deformation impulse. How we get this? So we can get this term alone by extending this to the right hand side, and this is to the left hand side. How to get this? By extending this to the right hand side and get this. And once we do this for particle A and particle B, because we can write the same two equations for particle B, but the difference is that this is going to be plus, not minus, you will find out that the restitution coefficient is equal to VB2 minus VA2 over VA1 minus VB1. So this is called the restitution coefficient. You're going to find more details in the notes how I got this. And let's talk a little bit about the restitution coefficient. Right, as I said, the restitution coefficient is VB2 minus VA2 over VA1 minus VB1. Okay, so let's try to have different cases of E. So let's say, what if we have a ball, like a soccer ball or a basketball, and it's hitting a wall, okay? So the ball has a velocity, How about the wall? Does it have a velocity? So VA has a value, but VB doesn't have a value. It's always equal to 0. So if there is no particle B, there's no particle B, which is the case that I said right now, so VB1 and VB2 is equal to 0. What is going to happen? E is going to be equal to negative VA2 over VA1. This is one case. The second case, what if E is equal to 1? What does it mean? What does it mean if E is equal to 1? I need you to, I just said it right now. I give you a few examples. It's plastic or elastic? Let's see. If E is equal to 1, this one. I'm just making a case. I'm going to remove this. What does it mean? That the restitution impulse is equal to the deformation impulse, right? Which means that F is equal to R, which means it's elastic. When the two hit each other, they are gonna leave because the same force is gonna do a reaction, okay? So that means it's perfectly elastic. Okay, so what if E is equal to 0? Plastic. Why? Because if E is equal to 0, that means that the numerator here is equal to 0. That means the restitution force is equal to 0. There's no restitution. So two bodies hit each other and then they are moving together. There is no restitution force that can make them leave each other, which happens when we have a crash. Okay, so E equal to 0, that means it's a perfectly plastic. And this means, like, if we're saying that E is equal to 0, that means that this term is equal to 0. VB2 minus VA2 is equal to 0, and that means that VB2 is equal to VA2 is equal to V. Okay? If this is equal to 0, that means that this term is equal to 0, and this term is equal to VB2 minus VA2, and is equal to 0, that means that VB2 is equal to VA2 is equal to V, which means that both bodies are moving together with the same velocity. Okay? Alright. That's the cases that we have here. Yeah, sure.
So that doesn't imply that velocity A1 minus, like velocity A1 and velocity V1 is equal to 0 too.
No, because if
Then it'll be undefined, right?
yes, it's gonna be undefined. If this term is equal to 0, this, so like, they are like, why? I need somebody tell me, like, if this term is equal to 0, what does it mean?
It's undefined.
What? I mean, like, what does physically mean?
You're defining it by nothing.
No, I'm not talking about the particle. Let's look at the particle. That means that VA1 and VB1 are equal. No, they are moving, but with the same velocity. They're not gonna hit each other. There's no restitution, there's nothing. So both cars moving with 60 miles per hour, so there's no way that they are gonna collide, okay? But we need to have one of them has different speed so that they can, yeah. All right. Okay, so let's.
Just so to be clear, one of the bodies have to be moving for this to happen.
Yeah,
When you stop that.
absolutely. If there's nobody's moving, so there's no impulse. But if like one of the body, like this is the case of like you have a wall and you have a ball, so one of them is
Yes.
moving, so make the restitution. Okay, so let's solve an example here. Let's make a quick one. You have a bar like this, let's say an example. And you have a body here and a body here. This is A and this is B, and mass A and VA1 and mass B and VB1. That's the R. Mass A is 4 kilograms and moving this way. Mass B is moving this way and it's 4 kilograms too. VA is 10 meters per second and VB is 5 meters per second. Okay, I give you all the initial conditions, all the initial velocities. I'm asking you to calculate the velocity of the two bodies if number one is E is equal to 0. I'm asking you to calculate the velocity of body A and body B if E is equal to 0. Is it easy or difficult when E is equal to 0? Why? Because both of them are gonna, like VB2 and VA2 is gonna have the same velocity V, so it's very, very easy. You don't have to solve for VA and VB2. How to do this? So first, you are gonna use this equation to get V, right? So you're gonna use this one to get V. So you're gonna say that MA VA1 plus MB VB1 is equal to the mass A plus the mass B multiplied by V, which is the velocity of both of them, like it's MAV and MBV, because I know that VA, especially for this case, VA2 is equal to VB2 is equal to V, especially for this case, not in general. Alright, that's a very easy one. I have MA is 4 kilograms and MB is 4 kilograms, so I can write 4 and I have VA is 10. And what should I write here? MVB. 10 plus or minus? Minus. Why? Because VB is moving the other way, so I should write -5. And here I have MA is 4 plus 4 multiplied by V, which I don't know. So V is going to be equal to 2.5 meters per second, and it's positive, and it's moving this way. And that actually makes sense. Why?
This one has more velocity.
Both of them have the same masses, okay? So no one has bigger masses that can give bigger momentum. Let's say if this body is 1,000 kilograms, not the 4, and have a velocity of 5, So absolutely, this body might have bigger momentum. Why? Because it's a 5 multiplied by 1,000, 5,000. But this one is 4 multiplied by 10 is 40. So it's gonna make this body move this way, okay? But both of them have the same masses. One have a lower velocity and one has a bigger velocity. So definitely both bodies are gonna move this way because this one is gonna force this one to move this way. That's how you judge your answer by yourself, okay? All right, so we have this 2.5 meter per second. Let's make it difficult. What if it's E is equal to 0.8? Does E has a unit? It's a coefficient, doesn't have a unit. Force over, impulse over impulse, yeah.
Can I ask you a quick question? I see to the left we have two equal, it says perfectly elastic. What does the perfectly plastic mean?
The perfectly elastic, like, that's what I said was the car crash. So if you have, let's not talk about car crash. If you have two bodies, and then they are gonna collide to each other, and they stick with each other, they don't leave each other and move as a one body. That's what is perfectly elastic. It happens with car crashes, it happens with asteroids when they hit each other, so there's something happening in space, and then asteroid hit a planet. And does the asteroid move in a different way, or both of them? Both of them stick to each other, and they don't move, or they move with the same speed.
And that's perfectly plastic.
That's perfectly plastic. But as I said, there's nothing that is perfect. Like, there's always like 99% or something. Okay, so, and actually that's what we do with the structural engineering. Sometimes I'm not sure, you guys had the statics, right? So in statics, you guys had the hinges, like hinge and roller, right? Like if you have a cross, something like this. And then we say that this is hinge and this is roller. You guys did something like this before?
Yeah.
So there is nothing that is perfect hinge and there is nothing that is perfectly roller. Because even if you have a cylinder, like a roller, that is moving, there's always a friction. There's always some F of friction down there. So we say that Fx here is 0. Fx is gonna be 0, even if this roller is moving on ice, there's still some friction. Okay? So Fx definitely has a value. But let's say if you have a value here 100 ton, and Fx is like 0.1 ton. It's very, very small that you can neglect it and say it's a perfectly roller. Okay? You are gonna say, okay, this hinge doesn't have a moment, it only have Fx and Y. No. When this rolls, there's some friction that happens. So there's nothing that is perfect. Okay, there's always something. Okay, let's get back to the problem. Okay, so what I was saying here, I'm saying that if E is equal to 0.8, the problem is gonna be a little bit complicated because both particles not gonna have the same velocity. So we need another equation. So it's gonna be the same thing. MA, let me not write the equation again. So I'm gonna have 4 multiplied by 10 minus 4 multiplied by 5 is equal to 4 multiplied by VA2 plus 4 multiplied by VB2. Okay? So this is the first equation. I have one single equation and two unknowns, VA2 and VB2, and I want to know both velocity. This was easy because I knew from E equal to 0 that both of them has the same velocity. This one is a little bit complicated. What I'm going to do next, I'm going to use E to find another equation because I know that E is equal to, has a relationship between VB2 and VA2. So I can say that 0.8 is equal to VB2 minus VA2 over VA1, which is 10, minus VB1. And VB1 is already negative 5, so this is going to be plus 5. So you can, VB2 minus VA2 is going to be equal to 12. And you have two equations, use your calculator. You guys know how to use the calculator to solve two equations, two unknown, and then you find VB2 and VA2. It's gonna be, VA is gonna be negative 3.5 meter per second. This one is 8.5 meter per second. All right, what if E is equal to 1? If E is equal to 1, I'm gonna replace this by 1, and VB2 minus VA2 is gonna be equal to 15, and you are gonna do the same thing. All right, so we are done with the easy part. What is the difficult part? Oh,
Is there any way you can move that monitor?
move what? The monitor? Okay, I'll try to. Right. All right, so there's different type of linear impact. It's called, the one that we did is called central impact. Central impact, if you have two bodies, something like this. And this one has a velocity this way, and this one has a velocity this way, and they are hitting each other. We call this the line of impact, and we call this the line of contact. Okay? So if the both velocity are in the direction of we call the line of contact or the plane of contact. So both of them are okay. So if the velocity are in the same direction of the line of impact, we call this central impact. But sometimes it's not. Sometimes our velocity is something this way. So this is VA, and this is VB. And our body start, for example, from here. So this is VA1, and this body start from here, and this is VB1. And after the impact each other, this body came here, and it's gonna have this VB2, and it's gonna have, sorry, this is
VA2.
A2 and VB2. So we call this oblique impact. So this has an angle, for example, theta, and this has an angle, for example, theta. It's kind of a little bit complicated. But all what we're gonna do is, we are gonna divide this motion into two bars. Let's take, this is body A, and this is body B. Let's see what's gonna happen with body A. So, over there. Okay, so let's look at the momentum of this body before the impact. So the momentum is gonna have a velocity this way. I'm gonna need to do the two components of this velocity. It's gonna have an x component and y component. So let's write, this is gonna have VA1 x direction, and another one in the, so let's write it off there. Okay, so the example that I did here is different than the example that I did in the notes. The notes is like the two poles is hitting each other vertically. I'm doing this one horizontally, okay? But it's the same concept, right? Okay, so let's write this one. So let's keep this one here.
And y instead of x.
This is x, no, because this is the example that we have. This is x and this is y. I'm gonna keep it this way. So this one is gonna have something this way, and one y direction, okay? And this one, particle B, is moving this way. So this way is gonna have something like this, and VB1, and if we analyze, so this is the other direction, so it's gonna be this way, gonna go up, M, V, V, V1, and this is in the Y direction. Okay, let's look at the impulse. Where's the direction of the impulse? Okay, so the impulse is only in one direction. Okay, there's no impulse in the two directions. Why? The impulse are always in the line of impact. The line of contact doesn't have any impulse. So we have impulse here in the X direction. So particle B has an impulse on particle A this way. So we are gonna have an impulse like this, the integration of F dt. Okay? And if we look at particle A impulse on particle B, so you are gonna have an impulse here at the integration of F dt. So this is gonna give us completely different things. So let's see. Yeah, so let's say this body is gonna move this way. So this body is gonna have two components and both of them are negative. So we're gonna have something like this, and this is M VA2 in the Y direction. And this is gonna be M VA2 in the X direction. And particle B is gonna move this way, so it's gonna have M VB2 in the X direction and M VB2 in the Y direction. So this is what happened. And the impulse are always in the direction of the line of impact. And the conservation of linear impulse only can apply at the line of impact. There is no impulse in the other direction, so we cannot apply the conservation of linear momentum in the with the impulse and momentum in the other direction. Okay, so let's look at this direction. We can write that the sum of the masses velocity v1 is equal to the sum of the masses velocity v2, and this is only can apply at the line of impact. So is the line of impact y or x? In this example, it's the x direction, but the one that you have in the notes is in the y direction. So it's good that you have two examples to look at. Okay, so I have in the x direction, so I'm only gonna look at the masses and the velocity in the x direction, not in the y direction, okay? So I have the mass A multiplied by the velocity A1 in the x direction plus the mass B multiplied by the velocity B1 in the x direction is equal to the mass A multiplied by the velocity A2 in the x direction plus the mass B multiplied by VB2 in the x direction. So that's actually the conservation of linear momentum. That's what happens here. Because both these two cancel each other, okay? So this is the first equation that we have, and the same thing can apply for the restitution coefficient. E is gonna be equal to VB2, but right now we're gonna write x because there's only impulse in the x direction minus VA2 in the x direction over VA1 in the x direction and VB1 in the x direction. So it's the same thing, but we are gonna put x direction in the equations. Nothing is different. You just need to define or to identify where they are hitting each other, where the impulse is. If you messed it up, it's gonna be completely different problem. Like let's say that you said that the impulse is gonna go this way, like F is here, okay, or something like goes down. This is wrong. F, the only component is the x direction that makes impulse. Okay, so this is the x direction. Once you identify that, write these equations and put subscript x to all the values. Okay, all right. So this is the first thing. This is number one. So this is about the x direction, which is where the impact happened. How about the other direction? The other direction, there is no impulses, so the velocities are going to be the same. So the momentum in the other direction and the y for each value of these before and after is the same. Like here, MA VAY is going to be equal to MV VBY because there is no other impulses that can be included. Same thing sorry, MAVAY is gonna be equal to MAVA2Y. So I'm saying here that the momentum of particle A and B in the direction of the linear contact is gonna be something like this. So MAVA1 in the Y direction is gonna be equal to MAVA2 in the Y direction. Same thing with body B. MBVB1 in the Y direction is gonna be equal to MBVB2 in the Y direction. Okay, so if we have oblique impact, you have to do two things. First, to identify the line of impact and the line of contact, and the impulse and the conservation of linear momentum is gonna be applied in the direction of the line of impact. So you're gonna write the same equations that we have and then put subscript x. And the other direction, the velocities are gonna stay the same. So from this, we can say that VA before and after VA1y is gonna be equal to VA2y, and VV1y is gonna be equal to VV2y. Just to mention, not the velocity of A1 is equal to the velocity of A2. I'm only talking about the component in the Y direction. The component in the X direction is gonna be the difference. And that's what it changes the total velocity. Okay? All right. So let's solve an example of this. Is it difficult? The oblique one, it's kind of confusing. But if you focus and identify the line of impact and subscript this with the line of impact subscript, so you put all the x's because the x is the line of impact. So you're gonna have these two equations, and this one is simple. Y component is gonna be the same. All what I'm gonna figure out is the x component. How much it's gonna be. And once you figure this out, the final velocity is gonna be Vx in the I direction plus Vy in the j hat direction. Then you can get the root, and then you can get the final velocity. All right, so let's see this example. You have an inclined wall like this. So you have this wall, and the angle, and then you have a body or a mass at this level, and it's gonna fall and hit the wall here, and this distance is 1 meter, and the wall has an angle that we can get it from this triangle, 3, 4, so we can get the theta. This is the body. So I'm saying that we have a 0.5 kilogram mass, so m is equal to 0.5 kilogram. Drop it from 1 meter for at rest, so the velocity here is equal to 0, V naught. On a surface that has E, so this surface has E, restitution coefficient of 0.75. What is the post bounce velocity expressed like here when it hits? What is the post bounce velocity? Well, I expect when this body hits, how's it gonna move? Yeah,
To the right.
it's gonna be like something like this, right?
Yeah.
That's how I expect. So all what I found is, what is this velocity that this body is gonna move with? Okay, so I can find the x component and y component. But actually, it's a better that I find it actually in tangent and normal, and that's what he's asking here. So I need to find a component in the normal direction and in the tangent direction. So if you found this velocity, you can get the components. How? Because we know the angles. Like if this angle is theta, this angle and this angle is 90 degrees. Why? Because this is 90 degrees. Oh no. Tangent. Okay, so this angle and this angle is 90 degrees, and this angle and this angle is 90 degrees, so I know that this is theta. Okay, so then this angle up there. So I can know from the angles I can get the velocity v. Right, so let's start solving this problem. The thing is, I'm telling that this is the velocity VO is equal to 0. And I want to use the this equation, the like before and after. So if you guys recall, what is the equation? This one. Right? So this is the impact. But the thing is, it's not x and y, it's tangent and normal. So where is the line of contact and the line of impact? Saying that, okay, let's make it easy for you. All right. It's not perfectly in the middle, so it's something like this, and this is the ball. Okay? And let me draw. Something like this. So this is the line of contact, and this is the line of impact. So I will apply this equation in the tangent direction or in the normal direction. So this is the tangent and this is the normal. So how I'm gonna apply this equation? This one was direct, like x and y, and I know that the line of contact, this one, this is the line of contact, and this is the line of impact. So I know that the line of impact is x, so I apply it in the x direction. Here, the line of impact is the tangent or the normal?
Normal.
Is in the normal, right? This direction. So I apply this equation in the normal direction. So I can say that m a1 in the normal direction plus m, let's say m a v a1 right here, m a v a1 in the normal direction plus m v VB1 in the normal direction is going to be MA VA2 in the normal direction plus MB VB2 in the normal direction. I write the equation, the momentum before and after is equal, but what I did, I put them in direction because this is the line where the linear momentum is conserved, okay? But there's a special case here. What is it? The one that we talked about here. If there is no particle B, there is a wall that doesn't move, so the velocity is equal to 0, so there is no particle B, right? So B is not moving, and B is not moving. So this one is equal to this one, and that's very easy. So right, so here we have MA VA1N equal to MA VA1 VA2N. And that's n cross, so VA1 in the normal direction is going to be equal to VA2 in the normal direction. Alright, so let's find VA1 in the n hat direction. How we can find it is, I'm saying that this particle is start from rest. So V naught is equal to 0. Do you think that V1 is equal to 0? Why? So what is, when I say V is equal to 0, this is not the V at the initial impact. The V at the initial impact when just right it hit the wall, not from here. Okay? Just at the head. Okay? So I need to find the velocity when this pole hit the wall. How can I find it?
Mass times gravity.
I need to use some of all the stuff that we learned it before to do that. So you know the distance, and then I know the velocity. You can do it in many different ways. I'm gonna use the conservation of energy. So I'm gonna say that the half mv1 squared plus mgh1 is equal to half mv2 squared plus half, plus mgh2. If you guys remember, the kinetic energy plus the potential energy is equal to the kinetic energy and potential energy at the final location. So this is the initial one, and this is the final one. I want to find the velocity here. Okay, it starts at v1 is equal to 0, so that means I can't cross that. And if I'm saying that this is my datum, so what is the mgh is equal to? So I have the body is equal to 1.5 kilogram multiplied by g 9.81, and h1 is 1 meter. Okay, so I got mgh1 half 0.5 v2 squared plus mgh2. When the body gets here and the datum h is going to be equal to 0, so this one is going to be 0. So what happened? The potential energy at position 1 is converted to kinetic energy at position 2. So I can't find the value of v2. So when you find the value of v2, it's going to be equal to 4.429 meter per second. What is v2? Is the velocity just before the impact, okay? But, and this is actually what I'm asking for. It asks what is the post-bounce velocity expressed in tangent and normal, okay? So this velocity actually is in y direction. So if I want to write it as a vector, v2 vector, it's going to be 0 in the I hat direction plus 4.429 in the j hat direction. That's not what we are asking for. We need to find the velocity in tangent and normal direction. So I need first to convert v2 tangent normal. So I need to find, like, this is my body, and so this is the wall, and this is v. I need to convert this v to one component in the normal. So I need to find vn. I need to find v tangent. Okay, I need to find both of them. All right, how can I do this? I need theta. So actually, as I told you a few seconds ago, if this is theta, this and this is 90 degrees, and this are 90 degrees, so this angle is theta. So if I want to find sine theta, you guys can tell me what is the sine theta here, given this triangle? 3, 4, 5.
4 over 5.
It's going to be
4 over 5.
4 over 5. And what is cosine theta?
3.
3 over 5. Okay, we got that. Alright, so if I want to find the Vn, so the velocity v, the same v, is going to be equal to Vn is equal to v2 sine theta. So I have v here as a value, so this is 4.429. So let's not find the normal verse, let's start with the tangent. The tangent is the sine component, and it's in the positive direction, so this is the tangent, this is the normal. So it's gonna be v, which is 4.429 sine theta, and sine theta is 4 over 5. And it's in the tangent direction, plus the v, but actually the normal direction is in negative n hat, so I'm gonna make this negative, and it's 4.429 multiplied by the sine component 3 over 5 in the n hat direction. So right now I have velocity in the direction of the line of contact and in the line of impact. So I have the velocity in the n hat direction and in the tangent direction. Which one that I can use for this equation is in the normal direction, the one in the line of impact. So I can use actually E. So I can write E as VB2, and I'm gonna write N right away, like right now, but I'm gonna make it a different color, and here VA1 minus VB1. And this equation is only applied in the direction of the line of impact, in the N direction, so I have to put N after each one. Like the same thing that I did with X here, EX, this one has XX because this is the line of impact. So body B, there's no body B, it's just a wall, has a velocity of 0, so this is 0 and this is 0. And it's a given in the problem that E is equal to 0.75, so it's gonna make it more easier, so I have 0.75 equal to negative VA2 n direction, which what I need, over VA1 in the n hat direction. I have the n hat direction. It's a negative 4.429 multiplied by 3/5. And I can get from here VA2 in the n-hat direction. So this is gonna be equal to 1.993 meter per second. All right. So am I done? Yes, he's asking about the velocity. You got the velocity, but you only got one component in the n-hat direction. He needs the entire velocity vector, the n-hat, and the n component, and the tangent component. So we got the n-hat component. Let's get the tangent. The tangent, if you look up here a few seconds ago, we said that MA VA1 is equal to MA VA2 in the direction of the line of contact. So a few minutes ago it was X, right now it's going to be the tangent direction. In the tangent, sorry, the math doesn't. Alright, a few minutes ago when I have all these drawings, it was MAVA1 Y is equal to MAVA2Y. Right now it's the tangent because we are working as a tangent normal direction. So right now I can say that MA, which is 0.5 kilograms, multiplied by VA1 tangent. VA1 tangent is equal to 4.429 multiplied by 4/5 is equal to 0.5 multiplied by VA2 tangent. So you can get V2 in the tangent direction. It's going to be 3.543 meter per second. So I can write the final velocity of the body that moved, like the body that fold. So it has a component in the tangent, 3.543 in the tangent direction, plus the component in the n-hat 1993 in the n-hat direction. Okay, so it's something like this. The ball hit this way. This is the n-hat. So the n-hat is positive. So this body is going to have a component 1.993 in the n-hat direction, positive one, and a component here 3.343. So if you get the resultant of these two, is going to give you a velocity this way. So the body fold this way, the velocity this, and then it's going to move this way once you get the resultant, which is the 3.5 squared plus 1.9 squared, and then you can get the, if you want to get them an XY component, you can get this angle and this angle and get the I and J hat, but that's not needed in this problem, but I did it here. Does anybody have any question? This problem was a little bit tricky. Why? Because it wasn't in the XY direction, the same one that I put in the example. I just like, it's rather than having a ball falling on the ground, we made the ground like this. So we had to rotate the axes, the XY axis. Actually, you cannot, like this, you can call it something else, not normal and tangent. You can call it X and Y, X dash and Y dash, and work with the new axes that you have, okay? All right, so we are done with the impact bar. Right now I'm gonna talk a little bit something that we can, so that we can start with like for 5 minutes. Just I need to revise something with you. You guys know the scalar quantities and the vector quantities, right? Scalar, like the energy, something that it doesn't have direction, okay? Like mass is 10 kilograms. We cannot say that the mass is in the X or Y direction, but the velocity is in the X and Y direction. And you guys know about the scalar product and the vector product. So what is the difference? Like if we are saying, we talked about X vector dot Y vector. Do you guys remember?
It'll give you a scalar.
Yeah.
It's gonna give us a scalar. What is the value of the scalar? It's gonna give you this the magnitude of X multiplied by the magnitude of Y multiplied by, like if you have a vector X and a vector y by cosine theta between them. And this one doesn't have direction. This one is gonna give you the scalar quantity. So you have a vector multiplied by vector. Dot product is gonna give you a scalar, not a vector. But there's something is called the cross product. So if you have x vector cross product y vector, what is the value of this? Let's talk about quantity, the magnitude, and then we will talk about direction. This one doesn't give you a scalar quantity, it's gonna give you a vector quantity. But let's find, so it has a magnitude and direction. Let's find the magnitude. The magnitude is the x vector multiplied by the y vector multiplied by sine theta. So this is the quantity, as a direction is, okay, I, J, K. Because this is very, did you guys did this before? You know it, right? So if x direction is I and this is J, what is the direction of this? K. Why? Because it's the right hand rule. You will go from I, like you rotate from I to J, and then the direction of the dot product is gonna be in the K hat direction, okay? So this is kind of like a general rule, like if this is I, J, and K. If you multiply a vector in I direction by a J direction, it's gonna give you K. K by I is gonna give you J. J by K is gonna give you I. So if you're going this way, but if you're going on the opposite way, it's gonna give you negative. I by K is gonna give you negative J. K by J is gonna give you negative I. J by I is gonna give you negative K. Okay? So it's a positive clockwise. How? Like right now we did I multiplied by J is gonna give us K, right? But if we multiply J by K, like something like this, it's gonna go this way, so my finger goes down, so it's a negative K. Same thing. J, K is gonna give you positive I, but KJ is gonna give you negative I, okay? Alright, so this is the cross product, and this actually makes sense. So if you have x and y, and the angle between them is theta, so it always needs the perpendicular direction. So you only care about this projection. So, because what we have in here, like this quantity y sine theta, this is y, this is theta, this is y sine theta. That's what we did. So it's always the magnitude of x by the perpendicular value on this x, okay? So the component in the other direction is not gonna be included. Why? Because if y has an example, a component this way, let's say y in the I hat direction, and then you have another y, let's say y cosine theta, and you have y sine theta in the j hat direction. This is I and x in the I direction. But when you multiply I hat by I hat, it's gonna give you 0. Like if you have two vectors, this is vector I and this is vector I, what is the angle between them? It's 0. So sine theta between them is 0. So I by I is 0, j by j is 0, k by k is 0. It's always gonna have a value. They have to be perpendicular to each other. I by j or j by k or something like that. So this is something to think about. All right, so right now I'm gonna give you the exam sheet. So if you have any questions, stop by my office right now. If you have a class after this one. So Oscar. Oscar? No, yeah, stop that.